In the past, we learned that if your first derivative was positive, it meant that your original function was increasing. And if your first derivative was negative, it meant that your original function was decreasing. Now we're going to do one more derivative, and then we're going to check the value to see if we get a positive or a negative. If your second derivative is negative, it means that your original function is going to be concave down. So you can be concave down increasing, or you could be concave down decreasing. So there's two types of concave down. I want you to notice that it's kind of like a bowl that's upside down. So that word down keeps coming. Also, you notice it points down. Now, if your second derivative is positive, that means your function is concave up. Now, you can be decreasing and concave up, and you can also be increasing and concave up. So the concave up and the concave down is a type of curvature. It's how it's curved. Again, I want to point out for concave up, I want you to notice that it's pointing up over here. Now here's an example of an x to the third function. It looks like it's been shifted right 3 and up 1. But you'll notice that our second derivative would be negative over here because the curvature is concave down over there. And our second derivative should be positive over here because the curvature is concave up over there. Now at the spot where we change from concave down to concave up, we have a point that we're going to call an inflection point. At that spot, the second derivative is going to be 0. But the reason why we call it an inflection point is because we change concavity. So you can change from concave down to concave up, and that point will be called an inflection point. Or you could change from concave up to concave down, and that point would be called an inflection point. Okay, we're going to take a look at another example, but I want to point out the difference between this one and the next example. On this example, the inflection point happened at a spot where the second derivative was equal to 0. Now we're going to go look at the next example. On this example, the inflection point is happening where the second derivative is undefined. So it kind of reminds you of when you do the first derivative test and you have that critical number. Remember, for a critical number, you're looking for anywhere that your first derivative is equal to 0 or anywhere your first derivative is undefined, and that's your critical number. So it's a similar kind of thing for the second derivative. When you're doing the second derivative, if you get a slope that's 0, or if you get a slope that's undefined, that could be a spot where you have an inflection point. Now, I do want to point out that at that spot, we do have a tangent line. It's just a vertical tangent line. So that's going to be one of our requirements in order to call it an inflection point. You have to have a tangent line, even if the tangent line is vertical. So if your function did something like this, it's kind of like the shark fin example. At that point, we are not going to say that it's an inflection point, and that's because there is no tangent line at that spot. Even though it changes from concave down, it's concave down here, to concave up. You'll notice it's concave up over there. So we will not call that an inflection point, and that's because there is no tangent line at that spot. So over here, we do have a tangent line. It's a vertical tangent line. So we're going to go ahead and say, yes, this is an inflection point. And again, that's because we changed from concave up to concave down at that point. Plus, our graph has a tangent slope at that point. For this example, we do change from concave down to concave up. That happens at x equals 0. However, we don't even have a point at x equals 0. So we definitely don't have a tangent slope at x equals 0. So we do not have an inflection point at x equals 0. Remember, your graph needs to have a tangent slope at that spot in order to call it an inflection point. And you need to change from concave down to concave up, or from concave up to concave down. So that means your second derivative has to change signs. In this case, we changed from negative to positive. So if your second derivative changes from negative to positive, we would say, yes, it would be an inflection point if your graph had a tangent slope at that spot. In this case, our graph does not have a slope at x equals 0. So x equals 0 is not an inflection point. Okay, now we're going to take a look at an example where we have the second derivative already solved for us and it's already factored. So we have these three factors here. The first thing I want to point out is that our second derivative will equal 0 if x is equal to 3, if x is equal to negative 2, or if x is equal to positive 9. What we're looking for is we want to see if our second derivative changes from either positive to negative or from negative to positive. If that happens, there's a good chance that we will have an inflection point at that spot. I want you to notice that our second derivative is just a polynomial. Remember, polynomials are differentiable everywhere. So we will have a tangent slope everywhere. So that means if our second derivative changes signs, then the spot where it changes is going to be an inflection point. Now we're going to fill out our second derivative chart almost the same as we did for our first derivative chart. On the bottom, we're going to put our numbers that make our second derivative 0. We're not going to call them critical numbers because this is not the first derivative test, but we're going to treat it like the first derivative test. Then we're going to plug in values in between. We're going to plug them into the second derivative and see if we get a positive or see if we get a negative. Let's start by plugging in a 10. If I plug in a 10, I get, and it doesn't actually matter what the number is. What matters is that it's positive. So I'm getting a positive for my second derivative when I plug in a 10. Now there is a trick for this piece. This piece right here, because it's squared, it's always going to be positive unless we plug in a 9. Since this piece is always positive, we can kind of ignore this piece. And really, we just have to plug into these two pieces here. Now, I already said we're ignoring this one because it's always positive. But something else is happening at these spots. Because they're odd powered, anytime it's odd power, it's going to change at that spot. So it's going to change at x equals 3, and it's going to change at x equals negative 2. So when I get to x equals 3, I'm going to change. So I'm going to change from positive to negative. I'm also going to change when I get to negative 2. I'm going to change from negative to positive. So anytime you have an even power, right here we have an even power, it's not going to change. So when I get to x equals 9, it's not going to change. So it's going to be positive, and then it's going to stay positive on the other side. So really, all you have to do is plug in one of these values. I plugged in a 10, and I got a positive. And after plugging that in, just look to see if the power is odd or even. An even power is the same on both sides. These odd powers will change. So when you get to x equals 3, it's going to change from positive to negative. And when you get to x equals negative 2, it's going to change from negative back to positive. Or what you could do is you could do it the slow way and just plug in values that are in between. That's the slow way, and it will take longer. Remember, if you're taking the AP test, time is everything. You want to do it as fast as you possibly can. So these little tricks are going to help you solve the problem much faster. Now, what is the meaning of your second derivative being positive? Well, it means your original function is concave up. If you're taking the AP test, be very careful not to say the word it. Don't say that it is concave up. You need to say that y is concave up when y double prime is positive. When you say the word it, they start to take points off. So now that we're talking about a lot of different functions, we have y prime, and we have y double prime. We have all these different functions. You have to be very careful not to say the word it. What we want to say is that when y double prime is negative, that means that y is concave down. And when y double prime is positive, y is concave up. Now remember, the question's asking for all the inflection points. In this case, we have an inflection point when x is equal to negative 2. And that's because we changed from concave up to concave down at x equals negative 2. We also have an inflection point when x is 3, and that's because we changed from concave down to concave up at x equals 3. Now, we won't be able to find the y value unless we have the original function. So for this example, they would most likely just be asking, where are the inflection points? So the inflection points are at x equals -2 and at x equals +3. Okay, if you were taking the AP test, you might get a question like this in the calculator section. And in the calculator section, most of the problems don't even need a calculator. So they're expecting you to know when a calculator is a good thing to use. They're giving us the function y equals sine of x squared. And they want to know how many inflection points does this function have from -pi to +pi. Now, I'm going to show you how to use your graphing calculator. In our class, we use the TI-89, so we'll be using that. And you're going to get something like this picture that we see right here. I think this picture was used using Desmos, but this is the graph of the second derivative. And we're only looking at it from -pi to +pi. Now, because we're looking for inflection points, we want to find where our second derivative changes from positive to negative. So our second derivative is going to be positive when it's above the x-axis. So it's going to be positive here, positive there, positive there, positive there, and positive there. That's where our second derivative is positive, and our second derivative is going to be negative below the x-axis. So the blue part is where our second derivative is negative. Now the spots where you change from being positive to negative, or where you change from being negative to positive, those are inflection points. So every one of these points would be an inflection point on your original graph of y. I'm counting 8 points, so I would say that y equals sine of x squared has 8 inflection points on the closed interval from -pi to +pi. Now let's see how we could get this graph with our graphing calculator. Okay, now we're going to look at using our TI-89 graphing calculator to solve this question. First thing I want to do is I want to find the second derivative. And so my function is sine of x squared. So I want to do the derivative of sine of x squared. Derivative is going to be blue and then 8. I want to do the derivative with respect to x. So I'm going to do comma x and put the right parentheses. Now if I go back inside, I can type in the function. My function is sine of x squared. Sine is going to be blue and y. It only gives me the left parentheses, so I need to put the right. Then I'll go back inside and put x squared. Now if I push enter, it's going to give me the first derivative. Let's have a look. That's the first derivative. Now if I want the second derivative, I can put a comma 2 after the x, and that'll give me my second derivative. There you go. That's the second derivative. Now what we want to do is we want to store that as a function. If we look at our function right now, we're going to do diamond and then y equals. You'll notice there's nothing there. So we'll go back to the home screen, push home. Now what I want to do is I want to store this second derivative in my y1 of x function. So I'm going to clear this. I'm going to go up. I'm going to grab all this. So I just need to push enter. And I'm going to store all of that as y1 of x. And when I push enter, it will store that second derivative in y1. Let's go take a look. Green and y equals. And there it is. My second derivative has been inserted for the y1 function. And now we can graph this, but I want to graph it from -pi to +pi. So I'm going to go to window, so diamond and window. My x min is going to be -pi. Don't forget the negative is not the same as the minus. The negative's below the 3. So negative. The pi is over here, but it's blue, so I got to push second. So I'm going from -pi to +pi. So now I'm going to push second and pi again. Now let's push graph and see what it looks like. Diamond and graph. Graph is going to be F3. Okay, now this is the second derivative, so it's the same picture we were looking at before. I think the picture from Desmos looks a little bit better. And that's how you'll do it with your TI-89 graphing calculator. Okay, one thing I want to point out is with the TI-89 graphing calculator, it was cut off a little bit. And that's because we only went up to 10 and down to -10. So if you want to see a little bit higher or a little bit lower, you might have to go up to 20 and down to -35. Let's go do that. So we're going to want to push window. That's the diamond. And then F2. we're going to want to go down and change the y minimum to negative 35 and the y maximum to be 20. And we'll push enter, and let's just graph it. Diamond, and then F3. Let's zoom in a little bit. Now we can see the entire graph, nothing's being cut off, but it is a little bit harder to see what's happening near the x-axis now. Okay, here we want to determine the intervals in which the graph of this equation is concave up or concave down. So we're going to start by doing the first derivative. Then we'll do one more derivative, and we'll factor it. Now the second derivative is not going to be undefined anywhere, but we do want to see where it's going to equal 0. Turns out x equals negative 4 and x equals 3. So we're going to treat those like critical numbers, even though they're not critical numbers, right? Because this is not the first derivative test. And we're going to choose numbers to plug in so that we can test in between. But we're plugging them into the second derivative. Remember, this is our second derivative. If I plug in a 10, I get a positive number. So my second derivative is positive when x is 10. That means my original function is going to be concave up when x is greater than 3. Okay, we just tested the value when x was 10. You could check when x is 0 and when x is negative 10, but that might waste a little bit of time. Remember, if the power is odd, it's going to change at that spot. So when x is 3, it's going to change from positive to negative. So that means your original function will be concave down, and at x equals negative 4, the power is odd, so the sign's going to change again from negative to positive. And that means your original function will be concave up when x is less than negative 4. You'll notice the second derivative changes from positive to negative at x equals negative 4, and it changes again from negative to positive at x equals positive 3. So those are the x values where you're going to have inflection points. Okay, if this question was asking for the inflection points, then you'd have to take these x values and plug them into the original function to get the y value. But they just want us to determine the intervals where this function is concave up and concave down. We've already done that. We are concave up when x is strictly less than negative 4 and when x is greater than 3. And y is going to be concave down when x is between negative 4 and 3. And that's it. Okay, we've already learned how to use the first derivative test to find a max or min, but now we're going to use the second derivative test to find a max or min. The way the second derivative test works is you need to have the first derivative equal to 0, and the second derivative must either be positive or negative. If you look at our first example, if your first derivative is 0 at this point, and your second derivative is negative, that means you're concave down, then you end up with a max. For our second picture, you can see the first derivative is 0. That's a horizontal tangent line. And our second derivative is positive, so that means you're concave up at that point. In that situation, you would have a minimum. Now, the second derivative test doesn't always work. If you get that the first derivative is 0 and the second derivative is 0, it could be any of these cases that you see right here. You could have a max, you could have a min, or it could just be something like this. So if this happens, if you get a first derivative equal to 0 and second derivative equal to 0, you just have to use another method to figure out if you have a max or a min. In that situation, I would just use the first derivative test. A good example of this would be y equals x to the 4th. It's going to be something like this. Looks like x squared, but it's a little flatter on the bottom. When you do the first derivative, you can see that the first derivative is equal to 0 when x is 0. Do one more derivative. Again, you can see now the second derivative is also equal to 0 when x is 0. So even though we know that there is a minimum at that spot, you cannot use the second derivative test to determine that there's a minimum at x equals 0 for that function. You would have to use the first derivative test. Okay, for this example, they want us to use the second derivative test to find the extrema for this function. Now, extrema means max or min. We need to do the first derivative, and then we need to see where our first derivative is going to equal 0. So we factor it, set it equal to 0. You can see the answers are negative 2 and positive 10. Now we need to determine what is the second derivative at each of these x values. So we're going to take our equation for our first derivative right here, copy it down again, And we'll do one more derivative, that's the second derivative. If you factor it, you can see easily that x equals 4 is where your second derivative is equal to 0, but we don't need to know where our second derivative is 0. We need to know what is the value of your second derivative when x is negative 2 and when x is positive 10. Well, you could plug in a 5 into your second derivative, and you'll see that you get a positive. You could plug in a 3 into your second derivative, and you see you would get a negative. So that means when x is negative 2, your first derivative is 0, and you're concave down. So that would give you a max at x equals negative 2. Remember, your first derivative is 0 when x is 10 as well. So that means the slope of your tangent line will be 0 when x is 10. And remember, you're concave up over here, so that's going to give you a minimum value when x is equal to 10. And that's it. That's how you use the second derivative test. Remember, you need your first derivative to be equal to 0, and your second derivative either needs to be positive or negative. If your second derivative is also equal to 0, then you cannot use the second derivative test to determine if it's a max or a min at that spot. You'd have to use the first derivative test in that situation. Okay, finally, our last example. They are asking if this equation has an inflection point when x is 1, then what is the value of a and b? Now, an inflection point could happen when your second derivative is undefined, but this is just a polynomial. So the only choice here is that our second derivative would have to equal 0. So let's do that. First derivative gives us this, and the second derivative gives us this. Now remember, we have an inflection point when x is 1. So that means y double prime of 1 has to equal 0. We can solve this, and we would get a equals 2. Now if we know that a is equal to 2, we can find b if we plug in a equals 2 and we plug in our point into the original function. So let's do that. So remember, I'm plugging in a equals 2, so that goes right here. I'm also plugging in x equals 1 from this point, and I'm plugging in y equals 10. Remember, we're solving this for b right now. Let's simplify it. 2 minus 11 gives us minus 9. Add 9 to both sides, we get b is equal to 19. Remember, they're asking us to solve for a and b. We already know a is 2, and we just found out that b is 19. And that's it.